Class again at 11:40. Okay. All right. So the next topic we are going to look at today is called state observer design. All right. So I think. Okay, that's the other one. I showed you how to design full state feedback controllers, all right? And we also looked at controllability, and we looked at observability. So the controller design has somewhat a dual side or a dual area that's called observers. So there is some similarities between a controller design and an observer, but they're working together. They must be working together in a seamless way. Can you shut down the door, please? Okay, so let me first state what we are trying to do here, okay? What we are trying to do. I told you that if this is, let's say, the system, the linear system, right? The output is X and the input is U. Now, we keep saying in full state feedback, well, I'm taking this X, I'm adding, I have a feedback gain matrix here, I add this, plus, minus, and it comes from here. Well, I told you we are cheating here a little bit because the real output of the system is not X unless you measure every X, right? The real output is Y. Okay, that's the real output. So this is a little bit cheating here. In reality, this is your output, and what you really should be doing is this. But this is what we call output feedback, and this is a little bit more involved than just full state feedback. Of course, you could say C is equal to identity matrix, and therefore X is equal to Y, and therefore instead of doing this, I'm just doing that. Of course, you can say that, all right? But the goal here is to do the following. The goal here is given U and Y, right? U is the input. U is the input that goes into the system. So that one we know, right? We can measure it. That's the one that goes into the system. That's the position of the aileron, the position of the elevator, the position of the rudder. So we know that. We measure that, right? So given that, given U, given Y, this is what we measure. Okay, given Y and U, question is, can we estimate X? So that's the question we are trying to answer today. All right? And this is something that we kind of have shown in observability, that the answer is yes if the system is observable. Sometimes what happens is some of the states are already measured, okay? Then you might use that measurement right here, okay? But some of the states might not be measured, then you need to estimate them. Sometimes all of the states you might be able to estimate using this. So this is what we call a state observer, okay? That estimates this X. So can we estimate X? What's going to happen here is, what we are hoping to do is to have a box here, which we will call the state observer. Okay? And the input to this box shall be Y. Okay? This should be the input. And it should be U. U should be another input. Okay? So U and Y. And the output of this should be an estimate of X. And I put a little cap here because X is just an estimate of X. Estimate of X, the state. What am I going to do with it? Well, imagine that I don't know anything about x, I just have some outputs y. I can use that x hat and send it over here as a feedback. Okay? And then my whole system will work with x hat. So this is what we are trying to do here. Design of state feedback. So the state observer shall estimate x using y and u. Okay, that's kind of the goal. So how does a state observer look like? Well, we can do a bunch of things. For instance, if you just had this model here, right, the state observer, if you just had an airplane, if you just had this in the airplane, right? If you know this model, if you know A and B around the equilibrium point, you could just send in U and then calculate X at each during flight, right? I'm just saying when you're doing, while you're flying, if you have this in your computer and I tell you what is U, you could estimate X during flight, right? I mean, you could calculate it on the way. But the problem here is, there are two problems here. One is, what is the starting point? You need a starting point, of course. The second problem is, what if something goes wrong here? How can I adjust this? There's no feedback that will adjust an error between the real and what's happening over here. So instead of this, what we are doing, we do the following. A typical state observer would look like this. We would take in U, put in the B matrix. Actually, don't need this. A times U, take an integral, you'll get X, right? Take that X, move it over here, make this one X hat, this one will be C, the output will be Y hat, okay? All right. Compare this with Y. Take this, say KE, and add this here. Or subtract it, sorry. Subtract it here. And the output of this would be that. That would be X hat. So the input here is U. To this red. Input is U. And the output, and another input here is Y. Okay? So basically what I've just plotted here, I will talk about this a lot more, is simply that. Okay? This is a state observer. Input is Y and U, like you see here. And the output of this is X hat. The output is X hat. So this is the architecture that we would call a full state feedback. I'm sorry, not full state observer. So this is a classic observer design. Okay, so how would this work? You would have your controller like we had before. Right? You would have your controller like we had before. The input would be U, output would be x, C, you would get y. This is of course given that D is equal to 0, okay? So you would take that U, it's in another color, maybe do it in red, the whole observer. So I take that U, send it over here, B plus minus integral A matrix C Y KE. That's that. Here we are getting Y from here. Here we are getting Y. Maybe I do this in blue. Let's do this one in blue. We're getting Y, and this one I can also do in blue. U, and this is K. This one will go here. R plus minus, and I'll just simply take this X hat. Okay? And the red stuff is what I call the observer. Okay? Its job is to take U, the control, the measurement Y, and estimate X hat. And this is what the architecture looks like. Here's the B, here's the A. It's basically, you know, here you have actually X dot hat. This is X dot hat over here, right? And then here you have X hat. And then you get C, and then you have Y hat. And then you compare it with your Y, feed back again K, add it back here, and you take the U, you take the A, and then you keep estimating this stuff. Okay? Now, this is the job here is really to estimate that. That's the idea. Now the question is, of course, can this estimate X hat? That would be a question, and I will show you now how show a proof that we can indeed estimate X hats. The second question is, what is this feedback gain K doing here? Well, it gives you some sort of a robustness in case that A, B, or any of these measurements are not doing well. Then this will help you to bring back the estimate of X hat to X. So our goal is to design KE. Design KE. Okay? That will be your job. Because if you have KE too large, then this would probably, you know, you take that error. This is now an error here. You see, Y hat minus Y. Right? The error here is equal to Y hat minus Y. Right? So if that error is too large and you have a large KE, then a very large number will come here, and then you take the integral of the very large number, and suddenly you have an X hat that is actually wrong. Right? If this is a large even if this is a large number and KE is very small, then you come back here and X hat will still be wrong as long as Y and Y hat are not exactly correct. So here's kind of the trick. If you have A, B, C on this side and you have A, B, C on that side, theoretically Y should be equal to Y hat, right? But there might be reasons why Y hat is not equal to Y. If Y is equal to Y hat, the feedback will be 0. It will be just A, B, C. This will be equivalent to this. Now in real life, of course, In real life, this is not what's happening. This is only the linearized model around the equilibrium point. In real life, this is really the aircraft. And it is, of course, nonlinear. Right? So this will never match this. I mean, this ABC is only valid at the equilibrium point of that aircraft. So while you are flying, this will never match that. So there will always be an error here, right? And so because of that error, this feedback will give you some sort of a robustness. Okay? Robustness meaning that it will converge back to zero, but it will never be exactly zero, that error, while you're flying, as long as you're not at the trim point. Okay? So instead of this, for now, let's stick with x dot equals ax plus bu and try to identify how we could possibly design KE, okay, to match this. Does this make sense, what I'm trying to do at least? Is that okay? All right, so let's write down the equations and see what we get. This is what we call an observer. KE is called the observer gain. Call the observer gain. Okay? So, this hat is an estimate, y hat is an estimate of y, so it is not exactly the same, so on and so forth. So, let's write the equations for this part, for the observer part, okay? So, x hat dot, or x dot hat, so it's an estimate of x dot, is equal to ax plus bu minus ke times y hat minus y. Is that okay? Y is the real measurement. U is the actual control that I know, right? So they don't have hats. Y is the estimate of the measurement, and x is the estimate of the state. Okay? Okay. So this y here is actually, it's like this. Ax hat plus bu minus ke y hat minus c times x, right? That's c times x, because y is equal to c times x. No, I can do the opposite. Let me not do that. Let me actually do this. We can do a plus over here, y minus c times x hat. Sorry, that's better. Okay, put a plus over here, flip these over, and this one is c times x hat. Okay, so finally, this will become a minus ke times c times x hat plus bu plus ke times y. So I just took this into the x hat parenthesis. A minus ke times c x hat plus bu plus ke times c times x. So now I'm writing this c times x. Okay? And this is what we call the observer dynamics. Okay? So this is the observer dynamics. You see that this x hat, now this is an equation in x hat. It's an equation of the estimation of x. Okay? This here is a hat. So it's the dynamics of the x hat. The real dynamics is this one. X dot is equal to ax plus bu. Right? That's the real dynamics of the system. call the real dynamics of the LTI. Or you might want to call it actual dynamics. I mean, real dynamics is a little funny word. Let's call it actual dynamics. Dynamics of ST. Okay. So define x minus x hat is equal to E, and okay, x minus x hat is E, so maybe you want to call this EY here. Okay, put a little EY here, denoting that this is the error of y hat minus y. I want to call x minus x hat equals E as a real error here between the states. All right. So if you define it like this, you can take the derivative of both sides, and you will get x dot minus x dot hat is equal to E dot. Right. If you take the derivative of both sides, that's what you get. Now, after you define this, subtract one from the other. Okay? Subtract the observer dynamics from the actual dynamics. From the actual dynamics. And let's see what we get. Subtract this from that, right? Then you will get x dot minus x dot hat, right? It will be x dot minus x dot hat is equal to the rest will be ax plus bu minus a minus ke times cx hat plus bu plus ke c times x. So this one here, no, it's here, it will be E dot is equal to, let's write this, ax minus ax hat plus ke times cx hat minus bu plus bu minus ke cx. Okay, subtracting this from that. So this will go, and you will have E dot is equal to A minus KEC times X minus X hat. And you will have X is equal to A minus KEC times E. And this is what we call the error dynamics. Error dynamics. That's what we call the error dynamics. So it is basically an equation for the error. What is the error? Error is this. Error is right here. That's the error. All right? Just write it down here so that we never forget what this is. This is x minus x hat. And if the error starts at a certain value, right, we want the error to go to 0, right? That's the goal. We want the error to go to 0 as t goes to infinity, right? I mean, this is a function in time, so I mean a differential equation, so therefore it is an implicit function in time. What you want is that as time goes to infinity, you want the error to go to 0. If the error goes to 0, then x is equal to x hat, and that is exactly what we're trying to do here. We're trying to estimate x hat. Okay? So any questions up to this point? Yes?
If you think of unreal airplane, with controller K and observer KE, are they corresponding to the same device, or there are different devices working separately?
What do you mean device?
In the beginning of the class you said that we can think the A matrix as an aircraft.
Yeah.
And
This represents the aircraft.
Yeah, and K represents the controller.
This is the controller that we are feeding back in the controller.
K is the device that's
it is a computer, first of all, right? There's a measurement here. There's a sensor that measures. Then there's a controller that multiplies that measurement with the control K and then sends it back to a control that is in between the pilot and the actuator. Okay? So that's that. That is, if you call this everything together a device, the sensor, the computer, and the actuator, yes, that's a device. Where is this happening? Well, this is usually happening in the computer itself. Okay? Because the computer is receiving control U and Y, right? And then it does calculations and sends back this information. So in the calculations, if you don't have X as a measurement in the computer, you can make this calculation to estimate X hat in the computer and then send it again back to the actuator on the aircraft. Okay? So just to remind you, this is the aircraft, and let's say you want to play with your, you want to change the position of the elevator. Okay? And let's say you have a pilot control. Let's say this is the longitudinal control. Okay? So, and the aircraft is of course doing maneuvers. Let's say it has a Q, like an angular rate. It might have a pitch angle, right? It might have a velocity, U, all this stuff that we have learned in flight dynamics. All right? So here's the little computer. Let me put the computer here, make it a little exaggerated big. Of course, a computer is not that big compared to an airplane. So you measure all these things into that computer. How do you measure? You have gyroscopes, accelerometers, lots of stuff. You measure these things, they go into the computer. So the computer then does all these calculations, take the measurement, do an observer, maybe multiply with X, okay, and then send that signal over here. Where's the pilot? The pilot is here. The pilot here is R. The pilot is playing with this R over there. Okay? The position of the elevator, that would be U. Okay? Normally the control is connected to the elevator. In old times it was connected through a steel cable, let's say. Or it is even to this day, we have airplanes where you have a steel cable where when you push this and the elevator will go up and down in small airplanes. Or you might actually have a rod, a metallic rod that will just push and pull. Okay? So that's how you move this elevator up and down. All right? So let's say for a moment that you have a rod. Okay? You have a rod where you can push and pull, a mechanism where you push and pull and the elevator goes up and down. All right? So the computer, what it would do is, it would just interfere with the pilot, and you would have something called, for instance, a serial actuator. Okay? A serial actuator. A serial actuator does this. It has two parts. Without the movement of R, it can move the elevator back and forth. You understand? Without moving the R, it is like a little piston here. It could move this elevator up and down. But if the pilot moves this R, this whole thing will also move together. So this whole thing will move together with this R. So even if the computer doesn't do anything, this will act like a rigid rod. Okay? But as the pilot moves this, this will start moving back and forth. But at the same time, the computer will tell this piston to move by itself, so it would just still move the elevator by itself. So the elevator would be U, as I said. The pilot would be R. And this is the conjunction, this one here. R, okay, minus that thing, K times X, which is here. This is K times X. Okay? Moves this thing, and this is equal to U, and U goes here. So if R doesn't move, if the pilot doesn't move anything, you still have this K times X moving here because of this. And if the pilot is moving the R, so you have R minus KX moving all to U. So this is something called a serial actuator. And this represents this conjunction over here. So question is, where is this happening? The observer. The observer calculations are still happening in this computer. Because the computer receives all measurements, and its job is to receive the measurements and give intelligent outputs to the serial actuator. And the serial actuator is this conjunction. And U would be the actual actuation, the position of the control elevator U. Does that make sense? I guess what I need to show you maybe next time is to show you pictures of serial actuators, or actually a video that shows how a serial actuator works. Which, by the way, these days you can do yourself. Go to YouTube and write serial actuator. I'm sure there will be something. Okay? Question?
Yeah. In this picture, where is the C?
There is really not a C. Okay? The C is here. This airplane is represented by AX plus BU in our model. I mean, this is what I would call a linear model of the airplane. So this linear model represents the airplane, and that's x that equals AX plus BU. Okay? Now wait. X is the state that we need to describe the motion of the airplane. That doesn't mean that we don't measure it. I mean, it doesn't mean we measure it, I'm sorry. It doesn't mean we measure it. The y equals c times x with d is equal to 0 is basically the measurement based on the states. So x are the states that we need to describe the motion. Y is the actual measurement. For instance, let's say for the longitudinal dynamics, I need these three, right? What else can I have? I need these three states to describe the motion, let's say, of the aircraft in the longitudinal state. In fact, I need one more. Which one is it? Which one? Omega? What is omega? Huh? W, you mean? W, right? Okay. This is the body axis U velocity. W is the body axis Z velocity, phi and phi. Let's say for the longitudinal motion of the aircraft, you need these four states to describe the motion. Without these two, can you describe the longitudinal motion? No. Basically, you can't really tell what the aircraft is doing. You need these four in order to describe this motion. Right? That would be your state. These are your states. You need them to describe the aircraft's motion. So what is Y? Y is what you measure. You might be measuring only these two. You might not have a gyroscope or an AHRS on your airplane, and you are just measuring, let's say, U and W. You don't measure these two. Let's say you don't measure them. Does this change the fact that you need these four states to describe the motion of the airplane? No. So you need four states to describe the motion of the airplane. However, you can have two measurements. Okay? Now the goal here, everything we have done over here is that What if we feed back the whole state, which means you measure all these things? What I'm trying to do with the observer is, let's measure only these two, but I need these four. How can I estimate them looking at these two? That's what I'm trying to do here. Okay? Does that make sense? Okay. So let's give a break. In the next hour, I will tell you how we calculate this KE here.